Alright, so in this video we are going to cover linearization process. So consider a non-linear system. So what is a non-linear system? It is a system that f of gx and f of g of xy and f of xg are given in terms of higher order variables, for example y squared, x squared, or as a product of these two. So if x star and y star is a fixed point, then it means that this should be satisfied. So this still the same way we find fixed points with linear systems as compared to the non-linear system. So still use the same method. However, to linearize the system, we make use of the Jacobian, and this Jacobian is supposed to be evaluated at the equilibrium point or at the fixed point. So the Jacobian of this system will be partial f, partial x, and partial f, partial y, partial g, partial x, partial g, partial y, evaluated at the fixed point. So let's look at an example. So obtain the linearized system of non-linear dynamical system below. So first of all, you need to have the ability to determine that this system is non-linear. Why? Because there is a product of x and y there. So this product makes this non-linear as compared to our previous examples. For some other cases, it might be that the y is squared or the x is squared or higher polynomials. So that can also lead to a system non-linear. Right, so the first step is to find the fixed point. So the fixed points, we equate these two right hand side to 0. So this would be equals to 0. So factor out x, so x is equals to 0. And then this one, factor out y, so y. So you can actually see that x here is 0, y there is 2, y is equals to 0, and then x is equals to 2. So when x is equals to 0, you can either use this or this equation. So when x is equals to 0, y will be equals to 0. So this is our first fixed point. Then using this one, y is equals to 2. So when y is equals to 2, x is equals to, when y is equals to 2, using this one, when y is equals to 2, if you use this one for y is equals to 2, for this one it will give you 0, because this y is equals to 2 is coming from these two equations. So for you to find the x, you need to use this side. So for y is equals to 2, there this will be 4 minus 2x, which give you x is equals to 2. So the fixed point there, another fixed point is 2, 2. So we've got two fixed points or equilibrium point, 0, 0, the origin, and 2, 2. So we linearize our system. So we have got f of xy given by 2x is equals to 2x minus xy, and g of xy 2y minus xy. So this is partial f, partial x, partial f, partial d, partial y, partial g, partial x, partial g, partial y. This should be evaluated at the equilibrium point. So if you differentiate this with respect to x, you get 2 minus y. Differentiate this with respect to y, you get, this is 2x with respect to y, so this is a constant, it will give you a 0. This will give you minus x. Differentiate this with respect to x, 2x this is more like a constant because it does not have x, so this will give you a 0. Differentiating this with respect to x, it will give you minus y. Differentiate this with respect to y, you get 2. Differentiate this with respect to y, you get minus x. So for the first equilibrium point, which is fixed point, which is 0, 0, substitute all these values for 0, 0. So the Jacobian will be given by 2 minus 0 minus 0 or 0, 0, 2. So that would be the Jacobian. Right, so from here you remember that for us to perform linearization we also have to change variables. So let's change variables as well to h and k. So this will be the derivatives of the new system, this will be the new matrix, which is the Jacobian, and then these are our variables. So in essence we want to come up with a new system in terms of h and k, which is linear. That's what we call the linearization process. We want to come up with a new system which is linear in terms of h and k. So our dh dt and our dk dt we have, and then substitute our Jacobian there, and then this is h and k. So if we multiply these two matrices, we get 2h and 2k. So therefore our system, our linear system at this equilibrium point is given by dh dt, which is given by 2h, and dk dt is given by 2k. Alright, so let's come up with a linearized system in terms of h and k at a, which is 2, 2. So at 2, 2, substitute this 2 on our Jacobian, this one, so this will be 2. So 2 minus 2, this will be 0, minus 2 minus 2, and then 2 minus 2 is 0 there. So this will be Jacobian will be 0, 0 minus 2 minus 2, then substituting for g there, and then multiplying, we'll get our system to be minus 2k minus 2h for this one. So these are our two linear systems. So if we have managed to come up with a linear systems or a linear system, that's when we can come up with the stability, or that's when we can then determine the stability of the system. Alright, so let's continue checking the stability of the nonlinear system. So as we did in the linear system, we have eigenvalues determined from this guy. So this is a minus this, so our a then becomes our Jacobian minus lambda, so this will be 0 minus lambda minus 2 minus 2, 0 minus 2, which is equals to 0. So this times this will give you minus lambda squared. This times this will give you 4 minus 4, which is the characteristic equation. Therefore our lambda, our eigenvalues are plus or minus 2. Since these two, the other one is positive and the other one is negative, we have a saddle point, a fixed point, which is a saddle point, and all saddle points are unstable. So this is an unstable equilibrium point which has got a special name called a saddle point. Thank you.